If a brake system with a master cylinder diameter of 0.4 centimeters and two slave cylinders, each with a diameter of 2 centimeters, were connected to a brake pedal in such a way that the pedal has a lever arm of 10.8 centimeter and pushes on the master cylinder with a lever arm of 1.8 centimeters, how much force is applied to the brakes when 80 newtons is applied to the pedal? And I'm going to concentrate maybe on that question first, but the second question is, if the pedal is depressed 3 centimeters, how much are the brake pads displaced? So this sounds like a somewhat complicated question. It's going to be helpful if I have a good sketch of it. Now, the actual master and slave cylinder part that is described here is the same as in the last example. So I've retained the sketch I had there with some parts taken away. But I'm going to add to this a sketch of what I think is being described for the brake pedal. So if I have like a brake pedal here, I'm thinking about a force being applied out here at some endpoint, and there'd be like, some kind of, you could say the fulcrum is maybe right here, or some kind of hinge that's holding it in place. And the distance from that to where the force is applied, that is a full 10.8 centimeter. But the distance from this hinge to where it is being applied to the master cylinder, that is 1.8 centimeters right there. So what that means is that brake lever itself is basically a lever that has a mechanical advantage. And the mechanical advantage is defined to be the ratio of the output force to the input force. But based on the way I think this ought to work, is it really should just be equal to the ratio of these two lengths. In other words, I think it's going to be 10.8 divided by 1.8, which is equal to 6. So mechanical advantage of 6. That means that for the braking system, I'm going to label the force right here. That force is really the input force for the hydraulic system. And so that force should be equal to the 80 newtons that was actually applied here onto the brake pedal all the way at the end of it, multiplied by the mechanical advantage, which gives me a total of 480 newtons. So with that information, I can now go and calculate what I think these output forces are. And the formula I'll use for that is F output is equal to the ratio of the output area divided by the input area multiplied by the input force. But just like in the last example, this ratio of areas can be boiled down to a ratio of the squares of the diameter. So this could look like 2 squared divided by 0.4 squared multiplied by this 480 Newton input force. And my calculator says that that is equal to 12,000 newtons. So that is the answer to the first question of how much force is applied to the actual, I think the interpretation is maybe to the brake pads as a result of 80 newtons being applied at the pedal. The second question, though, says if the pedal is depressed 3 centimeters, how much are the brake pads displaced? So the way I'm going to look at that is I'm going to first try to find out what is the input displacement to the hydraulic system. And I'm going to look at this in an intuitive fashion and say if there's 3 centimeters of displacement here, there's going to be a correspondingly smaller displacement here at the master cylinder that depends again on this ratio of these two lever arms, 10.8 and 1.8. And since it's smaller, I'm going to say it's 1.8 divided by 10.8 multiplied by 3 centimeters, which is equal to exactly half a centimeter. And then the output displacement for a single slave cylinder system, which is what the formula that we have on the key concepts page essentially is for. This is really a rearrangement of that formula, but it's the ratio of the input force to the output force multiplied by that input displacement. And this should make sense because we're usually applying a larger displacement here at the master cylinder, and the input force on the hydraulic system is 480 newtons. The output force is 12,000 newtons. So multiplied by that half a centimeter is going to give me a really small output displacement, which actually makes sense for braking systems. Usually the displacement that's there at the actual brakes is very, very small compared to the amount input, which is kind of like the trade-off. You get a much magnified force, right? A largely magnified force, but the trade-off is you have to put in displacement. That's kind of related to that whole concept of input work is equal to output work. However, this is not my final answer because there are two slave cylinders, and there's only so much volume of liquid that's being displaced here in the master cylinder. It's going to have to be divided up between these two cylinders, which means their actual displacement would be half of this. In other words, I'm going to say times half, reflecting the two cylinders, to give me an answer of 0.01 centimeters. So the two answers I have here to the question are the 12,000 newtons and 0.01 centimeters. So that will allow us to more easily check in this whole like chaotic page of numbers and calculations here, but that does appear to match up.